Well, hello there, and welcome back for more Advent of Code. So today we are following along where we left off last time. No, not this page, adventofcode.com. That will be day 8, and day 8 is called Treetop Treehouse. Nice, interesting. It's a bit late at night here already, and well, I don't know if I will be able to complete this challenge. If it is as complicated as the last one I did, then maybe not, and I will leave it for tomorrow, but hopefully it's a bit simpler, and if it is, maybe I can squeeze it today. Or I mean tonight, I guess. So let's read what this challenge is about. So, Treetop Treehouse. The expedition comes across a peculiar patch of tall trees, all planted carefully in a grid. My cat is making some noises. The elves explain that a previous expedition planted these trees as a reforestation effort. Now they are curious if this would be a good location for a tree house. Okay, and this is a Wikipedia article for a tree house. Yeah, look at that fancy tree house here. A treehouse in Papua. Very interesting. I guess people who grew up watching The Simpsons all have dreamed about having a treehouse at some point in their lives. So this might be a nice nostalgic reference. So first, determine whether there is enough tree cover here to keep a treehouse hidden. To do this, you need to count the number of trees that are visible from outside the grid. Okay, so this is a grid-based puzzle, which I pretty much like. So the number of trees that are visible from outside the grid when looking directly along a row or column. The elves have already launched a quadcopter. I guess a quadcopter is a drone. Yes, it looks like it. The elves have already launched a quadcopter to generate a map with the height of each tree, your puzzle input. For example, this thing. Alright, each tree is represented as a single digit whose value is its height, where 0 is the shortest and 9 is the tallest. Okay. A tree is visible if all the other trees between it and an edge of the grid are shorter than it. Only consider trees in the same row or column, that is, only look up, down, left or right from any given tree. Okay, so yeah, a pretty square grid. All of the trees around the edge of the grid are visible, since they are already on the edge. There are no trees to block the view. Oh, since they are already in the edge, there are no trees to block the view. Okay. In this example, that only leaves the interior 9 trees to consider. So, okay, in this grid of 5 by 5, only these 3 by 3, that means 9 trees could be hidden. And the top left 5 is visible from the left and top. So yeah, 5. It isn't visible from the right or bottom since other trees of height 5 are in the way. Okay, so if there is another tree of height 5 or more in some of these directions, then this wouldn't be, like in all of these directions, this wouldn't be visible, but since in 2 directions there are smaller trees, this is indeed visible. The top middle 5 is visible from the top and right. Yes, okay, cool. The top right one is not visible from any direction. For it to be visible, there would need to only be trees of height 0 between it and an edge. Okay, so yes, it makes sense. For all trees on one direction to be smaller than this, they should all be 0. Then the left middle 5 is visible, but only from the right. Okay, so these are all the examples on this 3 by 3 innermost grid. With 16 trees visible on the edge and another 5 visible in the interior, a total of 21 trees are visible in this arrangement. Consider your map. How many trees are visible from the outside the grid? Okay, and I guess the input will be a bigger grid. Yes. Okay, this doesn't look all that complicated, I think. It's probably some pretty optimized ways or clever ways of doing this, but I think a simple and naive solution could be enough. So let's start. Let's go to Advent of Code 2022, launch the editor. Oh, by the way, the previous day solution that I did in the previous video, I then tried to try out an alternative solution to that using an actual tree data structure, and I managed to get it working. So this one was about calculating sizes on a file system, the sizes of directories recursively, and blah blah blah. And well, in the previous video I managed to get a solution that was a bit hackish. Let's say it didn't really parse the file system into an actual tree, but it is compact enough and it works, and I actually like it. But I was then curious to try out if I could make it work to actually parse it into a tree, and I managed to get it working. So yeah, it's a bit more code. Actually, it's double the size, and it's more complicated. And yeah, parsing things into recursive data structures, it's not too easy. And walking this thing, typing this walk function, was also a headache or something that I had to learn. There's a lot of there are lots of things that I also needed to learn about. I think there are some ref. No, actually I didn't end up using ref bindings, but yeah, there's a thing in Rust called ref bindings, and I had to learn about that to come up with this, because this has some interesting challenges on mutable references. You have to keep a single mutable reference that you want to update while parsing. And it wasn't too easy, but in the end, the solution is not too bad. And if you want to check it out, it is on GitHub, and there's a link to that on the description. But yeah, that thing aside, let's start with day 8 solution. So let's create a new file, 8rs, and let's create a new input file, day 8 txt. So here we can copy the sample input. Yes, and let's also import this module and add it to the vector or the array of days. And well, let's try to come up with a solution. So let's start with the usual preamble here. We need a function that takes an input and returns a string output. So what are we going to do? Well, first we have to parse the grid into something, into some data structure, and then I guess, so the idea is to go tree by tree and see if there is a line of visibility to either the top, right, bottom, or left. I think that's it, and then count how many of the trees are visible. So yeah, let's try to go for a naive solution and see if that works. So first, let's parse. Actually, first let's reload the file to have proper indentation knowledge in the editor. So let's first parse this into some data structures. So where do we want to put it? I guess we can have input lines collected. Well, maybe we could have, let's say, let's grid B, and the grid, let's make it a vector of I guess we could use usize for the tree heights. So this would be a two-dimensional vector, and we can get all lines and then map them to, I guess we could have line as bytes, like the string for each line mapped to bytes. And actually we could have something quite simple. So bytes as bytes returns a slice of bytes, and I guess we don't need to have usize. We can have simply bytes here, and you know, this thing, they are characters from 0 to 9. So I guess we could do as bytes and then map. Now I guess we need to iterate over this, then map, and each of the bytes in here, which would be a character, I guess we could map it to, we could just, well, have that. Yeah, we could just have that, I think. Array of bytes, wouldn't that work? Well, actually, I could transform these characters to bytes from 0 to 9. So that would be doing like character minus the byte for 0. So, you know, this thing would be 0 for the character 0 and 9 for the character 9. And that should work, I think. So we have all of this, and then we collect into a vector. And for this, we also collect. And I think that should be the parsing. We can print line this and see if we got it right. Let's debug print it. Stick read. And let's run cargo run the 8s. Oh, not CD, that would be CH for character. The 8 doesn't exist because I had a typo there. I didn't see it. Let's try again. Okay. Does this look like the input? Yes, it does. Okay, so that was it for the parsing. Now, what should we do with these? I think, well, we are going to count things, so I guess we could iterate over all of these things and then do like a filter and a count of those things. But maybe I can use a good old for loop for this, and it might be more readable. So let's mute. We are counting the visible trees. And let's start at 0. And we are going to iterate this grid first. Should I go? Yes, maybe y coordinate first. Well, actually, I could use something like enumerate. Well, no, it's enumerate to have both the line and the coordinate at the same time. So this would give me a single line or row, I could call it. Yeah, let's call it row and column, I guess. And to Do I have the correct things? What is the row here? Why don't you know about this? Oh no, this is not. Yes, in this iterator. So row is the no, it's actually the other way around. So first comes the coordinates or the index, and then the inner row, and then we're going to do the same thing for x in this thing in row iter enumerate, and what we get here is basically the tree height. So yeah, we don't need to do like x and y, increment them manually and then indexing into the grid manually. We can have iterators for doing that work for us. So now that we have the tree height, we should check what is the condition. So if all of the trees on the left are smaller, or all of the trees on top are smaller, and so on. So it's an OR condition between like the 4 coordinates. So maybe we can put all the trees in each direction into like 4 different iterators. So let's say top trees. Well, let's start with the simplest one. Left trees would be what? They would be the trees that are in this row from 0 up to the x, where this tree, so tree height is the height of the tree at x and y, right? So we go from 0 to x, and those are the left trees. I guess we could have the iterator for this, and then have the right trees. This would be pretty similar, but we will start from x plus 1 up to, well, the end of this thing. Actually, I think we don't need the 0 here, pretty sure. And same thing, let's grab an iterator for this. Then the top trees, how do we get an iterator for those top trees? I guess we can do have to use the y coordinate, so we can get the grid and iterate over this and have the lines. Wait, no, actually we want to have the lines that are on top of this. So this will be grid going from 0 up to this y coordinates, and we can iterate over here and map this to this would be a row. Then we have the tree height that is on that row on coordinate x, right? Something like that. So let's see the types of this. This is an iter of u8. That's very nice. And this top trees is well, a more complicated iterator, but I think it's still an iterator over u8 values. So let's do now top trees, and so left, right, top, down trees or bottom trees. I don't know what sounds better there, but here we will start in a similar way from I plus 1 till the end, and we are going to map the same way. We're going to get the tree at the x position on that row. Okay, so now we do the condition. So if the left trees are all less tall than our current tree, like this tree height. So let's see, T less, or I guess this is a height, so let's call it H. H is less than tree height. Let's actually, well, let's then expand this condition, but we would do visible trees plus equals 1, like increment by 1. So it doesn't like this thing because maybe H is, yes. Oh, because it's not a mutable. So we are consuming these iterators, I guess, when we are doing this. So I guess it's fine. We can make this all mutable. So we're going to have this, and we're basically going to do the same, but for all of the other conditions. So, or the right trees are all less, or the top trees or the down trees. I don't know if these are the correct names that the example uses. And here I guess we are having some sort of reference thingy. So sorry, these H are references to U8, and these are not references. So I guess we could borrow, like take a reference here, and then this would be wrong, and I don't know if we could. I think this is fine. Well, let's just dereference here, and that's it. So do you like that? Okay, and let's just print the visible trees for now and see what we get. Formats the visible trees. Well, 21. Very nice. That is what the puzzle description said it should be for this sample input. So this actually works quite nice. Yeah, let's try out with the actual input and see if it works. Sorry, this would be day 8 txt. Let's save this and run again. So 1533. Let's try this out and see. All right, that was quite an easy one. Pretty glad. There's probably some things that we could do to improve this code, but let's read part 2 and see if there is what we need to do for the rest of the puzzle. Okay, so part 2 is a bit long. Part 2. Content with the amount of tree cover available, the elves just need to know the best spot to build their tree house. They would like to be able to see a lot of trees. To measure the viewing distance from a given tree, look up, down, left, and right. Sorry, I get distracted by something. It's not top trees, it's up trees. So left, right, up, and down are the directions. So we look up, down, and right from that tree. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. So the same height or taller than the tree, yeah, because that's if we are in the top of the tree house, we wouldn't, like when we have a tree of the same height, we wouldn't be able to look at more trees behind it. If a tree is right on the edge, at least one of its viewing distances will be 0. Yes, okay. The elves don't care about distant trees taller than those found by the rules above. Distant trees taller than the rules above. Okay. The proposed tree house has large eaves. What are eaves? Oh, okay. Eaves are these things on buildings. I didn't know that. Today I learned something. To keep it dry. Sorry, what is this about? The elves don't care about distant trees taller than those found by the rules above. The proposed tree house has large eaves to keep it dry, so they wouldn't be able to see higher than the tree house anyway. Okay. So they don't care about higher trees. You will see up to a tree that is the same height or higher, right? Okay, let's see the example. In the example above, consider the middle 5 in the second row, this thing. Looking up, its view is not blocked. You can see one tree of height 3, okay? Looking left, its view is blocked immediately. You can see only one tree of height 5 right next to it. Looking right, its view is not blocked. You can see 2 trees, so these 2. Looking down, its view is blocked eventually. You can see 2 trees, one of height 3, then the tree of height 5 that blocks its view. So looking down, you can see this tree, and then you can see this one. So you can see up to the one that is the same height or higher. A tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. For this tree, this is 4, found by multiplying 1 plus, times 1 times 2 times 2. Sorry, my cat is not complying, not helping. Okay, so you multiply all the viewing distances. However, you can do even better. Consider the tree of height 5, height 5 in the middle of the 4th row. So this one. Looking up, its view is blocked on at 2 trees. So here. Blah, blah. Looking left, its view is not blocked. You can see 2 trees. Okay. Then here it will also see these 2, and then so it will be 2 times 2 times 2 times 1, and that is 8. Okay, consider each tree on your map. What is the highest scenic score possible for any tree? Okay, that's interesting. What is the highest scenic score possible for any tree? So I guess we could reuse the same iteration, since we did a procedural, like imperative code of setting this variable and updating it. We can do kind of the same thing for the thing that we want to calculate now. What I'm wondering though is how are we going to do this? I think, well, okay, let's leave this calculation. We have the left trees, right trees, up trees, down trees. Yes. I can do something quite similar to this, but making sure to go in order from our tree to the edge, and yeah, so let's just copy this for now. We can then see how to maybe reuse these things. But so looking at the left trees, we need to start by like this is the same iterator, but going backwards, right? So we start from the x position and go back to 0. So if we reverse this iterator, that should be enough for that. Yeah. We can do this now for the right trees. This is fine. For the up trees, we need to do the same thing of reversing. And for the down trees, that is fine. Okay. So once we have this, we can do a sort of similar thing. Let's say, how is this thing called? Scenic score. Scenic score is gonna be, so let's start with the left trees, and we are going to, I think, take while would be an iterator to use. So we're going to take while the height is less than our tree height, I think. But maybe that's not correct, because that won't take okay, no, let's dereference here. I think that won't take the tree that is one higher, right? So take while, maybe we can see an example of this. Take while it is negative, so it will only take the -1, and then it won't take the 0. Yes, okay. So that's not what I'm looking for. And what would happen if we unconditionally add 1 to this, like to this calculation? It also won't work, because that would be wrong for trees that are on the edge, or that can see up to the edge. So, because I was thinking of doing take while of this and then calculating the count of this, I think, and then adding all up the different iterators this way. But we should also consider the first tree that is higher, or the same height. So how do we do that? Like, once we find 1, we stop. I mean, we could do an imperative function for this, and I'm tempted to do just that. So how would we do that? Let's say scenic score, let's start at 0, make this thing mutable. We have lots of mutable things today, and we will continue doing so. So we will do something like, well, we could maybe do left trees for each h, and do what do we want to do? Now, this doesn't make sense. Let's do an actual for loop. Man, I won't like this thing, but let's try. In left trees, let's do, we can consume this one, that's no problem. I guess we could do scenic score incremented by 1, and then if this tree is equal, higher or equal than the tree height, than our tree height, then we break, right? That sort of makes sense to me. So yeah, basically while the heights of these trees are, and actually we need to add these distances and then multiply it for the scenic score. So it's a bit involved. I surely would like to have something like take while plus 1. Could I cheese it somehow? I think I probably could. No, but let's not think about. Maybe we can repeat a little code. That won't be bad. We can see the patterns later. So this is not actually the scenic score. This should be like a mutable variable for saying like left view or something like that. Viewing distance. Let's call this thing then left distance. And we are going to do basically the same for each direction, which will be pretty ugly, but we have to do what we had to do. So the right distance, we're going to iterate the right trees, and we're going to do the same for the up and down trees. So up distance, we're going to iterate the up trees, and then the down distance, we're going to iterate the down trees. I already very much dislike this code, but that's okay. So what are you complaining about? They're referencing this borrow because this age is a U8. Of course, of course. Okay, and then the again, how was this called? Scenic score would be scenic score. It's going to be the left distance times the right distance times the up distance times the down distance. By the way, so one of these distances will be 0 when we are right against the edge. I think this was mentioned at some point. If a tree is right on the edge, at least one of its viewing distances will be 0. Yes, yes, that makes perfect sense. Okay, so this is the scenic score. I'm already thinking about how to improve this code, but let's not do that now. Let's instead actually come up with the best scenic score. So to do that, let's have another mutable variable. So best scenic score would be, we can start with 0, and here we could do, if the scenic score is greater than the best scenic score, then assign it. that's fine. Another way of doing this is saying best in score and max another one, like get the maximum of the two. So yeah, this is basically the same. Okay, and let's print it and see what comes up. We can try out the sample input first. Let's run. Okay, it said 8, and that was what we had in the example. I have no idea. I would be very glad if I can get this right from the start. So the actual grid is 99 lines, and where are the columns? 99 columns also. So that's pretty big. And let's print this now. And it's this number. Did we get it right? Yes. Very good. Let's see the advent calendar drawing. Okay, so there's a new thing here, some golden thing. I have no idea what this is. Doesn't look like a treehouse. Oh no, I don't want to go there yet. So okay, that is a correct solution. And this is a very repetitive code, and here it is saying that it doesn't need to be mutable. Why not, though? Why not? I guess because we are then consuming them like in for loops, and these things get moved. That is fine, I guess. Yeah. So this is pretty ugly, yes. And it's uglier than this part, the first part, I guess. I think we can improve both of these in some way. So, viewing distance. And we can also have the visibility. Like, are these two things related somehow? So, if the viewing distance for a given coordinate is the same as like the distance from that to the edge, we know that the lighthouse, the treehouse, would be visible. So we could relate these two actually. And would that be any good for us? Maybe. We have these distances. How could we remove a little bit of this ugly repetition? I guess another approach to this could be indexing into the grid and having like an array of the 4 directions that we can move in, and treat this thing in a more generic way. So let's first add this to Git to then make any improvements. Okay. I mean, it's a bit of repetitive code, but it is readable, I guess. Or it's that simple what it does, so that's good at least. this use of iterators is maybe a bit too clever, maybe. So, let's see. What if we do something less clever than this? We could trying to think of a better way. So what I'm thinking about is something like having, let's say, let up be something like how do you go up? You move, thinking of xy coordinates, you move 0 in the x position. I guess the first, if we want to index the grid, that would be, first coordinate would be the y coordinate. So maybe a bit. Let's follow the xy convention here. So we move 0 in the x coordinate and -1 in the y coordinate. Down would be similar, but we move, we increment 1 here. Then left would be moving -1 here, and then right would be this. Okay. Then we could also have an array of these things. Let's call it directions. It's gonna be up, down, left and right. I don't know why I used this order and here I said left, right, up or down, but I'm going to stick to this. We can move these non-mutable things to the top here. Can also use correct spelling. Okay, I can probably declare these things as const, like on the top of the file, but usually declaring these things as local variables is easier because the Rust does type inference for these things, and you don't have to like manually type each variable. So, okay, and I guess we could replace this kind of iterators by going in each direction and checking if all of the directions yeah, so let's try to first maybe replace the visibility code and see if it works. So how do we check this actually? We are also going to need to do some bounds checking, which we haven't done any of that in this code. Like this existing code is quite nice in the sense that since we are using iterators for all of this and we are using slices, it's very convenient. Like you don't need to do any bounds checking of the variables. So now I think if we are going to start moving in these directions, we have to check bounds to break those loops or something like that. So yeah, maybe that's not the best. I'm probably missing something really obvious here. Here we add one and we break when we are out of these. Sure. So okay, let's try to maybe replace this uglier code and say something like okay, let's comment this thing and say something like what? Like directions. So we're going to calculate the viewing distances. So let viewing distances be directions, and I think we can just map, because directions is a static array, so we can map a static array and we are going to get an array of 4 here, if I'm not mistaken. So we can map these directions, so let's call it dx and dy, and we're going to do what here? So we're going to move in this direction. So so what do? We can do a, I think in Rust while true is, no, I think there's a loop construct, yes. We're just going to loop and see. Actually, we're going to start at x and y, which would be these x and y. Yes, so let's say let x and y be these x and y. So this is a magic trick of Rust, I guess, that I apparently don't know how to do. So yeah, we can basically declare new variables with the same name, and they are going to shadow the variables, the outer variables, but we are going to use these ones for this loop, but they are not going to change the outer variables. So yeah, it's a shadow plus making this mutable. So what are we going to do? We are going to start there, and we first, I guess, we need to increment these things. So x, we are going to add dx, and y, we are going to add dy. And what were we doing? We are doing this distance calculation. So here we are looping over this, yes. Then we could say what? The we're going to count, right? So this is going to be let's distance be 0, and again another mutable thing. At least we are trying to like reduce these 4 very imperative loops into one very imperative loop. So you know, we it's like putting the garbage behind below the carpet, like hiding it into one ugly loop. So okay, if the tree that is at grid y coordinate, and actually we have to do some bound checking before doing this access, but okay, if this thing is greater, so I guess if it is greater or equal, we're going to do kind of the same thing. To tree height, this is going to be the break condition. But let's first bounce check this thing. Why don't you like this? Because you need some dereferencing, of course. So actually, in order to do bounce checking, we need to also know the dimensions of our grid, which we haven't done before. Oh, this is inferring this to be a U size, but it shouldn't. It should be. So bummer. We have to do some type corrections here. Yeah, that's not very cool. Let's actually inline this variable, inline this variable, inline this variable, and inline this variable, such that we can declare the type only once here. And I say that this is a vector of E size, I guess, and infer the length. We don't like this. Oh no, these are tuples. Well, I guess we could use I32. And don't you like this? What don't you like? Expected this slice? No, yeah. Can you infer this thing? I don't know why like inferring static arrays is not like this is pretty much that the compiler should know this. Anyway, so here dx and dy, yeah, we cannot add this willy-nilly to this, so I guess we could use, these are U sizes, we could cast here side32, because we are going to be adding possibly negative numbers to this, so this need to be signed. But now let's do the bounce checking actually, which is what I wanted to do in the beginning. So we have the grid. We can also have the heights. Well, we could call this height is a conflicting name because we are talking about tree heights. So let's call it grid height. It's going to be the grid length and the grid width. It's going to be grid's first line length. Okay, so how do we do the bounce checking? So if I guess we could use a range. So this is the width. So if this thing doesn't contain x, so if x is not within that, or same thing but for the height. My cat is going bonkers. So if either coordinate is out of bounds, we break. Sure. And we can access this with confidence. But also, what did we want to do? So if it's not out of bounds, well, it means that it is a tree that we can see. So the distance, this distance, we can increment by 1. We can actually call this thing viewing distance. So, and here we were we are inside a map, so we can return this viewing distance very well. And viewing distances will be, yeah, an array of 4 numbers. And here the scenic score, we can multiply these viewing distances together. So viewing distances, we can just as there is a sum. Is there a multiplication? Not really. I guess we can fold. Well, we have an initial value, but we don't need. Is reduce something similar? But yeah, no, I think fold is correct. Here, I don't want to deal with optionals or something like that. So yeah, simply multiply these 2 things together. A times B, and that's it. So our previous answer was this. Let's see what happens if we run now. Of course, we exploded. Oh no, there are still some errors here. Where are these errors? Oh yes, slicing with bad types or mismatched types. So yeah, here this thing cannot contain because it was expecting a U size, but I guess X and Y. Can't this be a grid width as I32? Wouldn't you be happy with that? And also this, and here this and this. I'm not really liking this very much. And what other problem was there? Why don't you like this? Oh, you need to borrow this thing, right? Yes, okay. Sure. And then the indexing. So now we know that these should be within bounds, so we can here cast them again as usize. Not the prettiest code so far. Okay, we got an answer, and I think it was the same answer that we had before. You can check. Yes, it looks like it. So okay, we transformed like 4 loops into this giant map and loop. That is not really very nice looking, to be honest. So well, but one thing that we can know is that maybe we can combine this viewing distance calculation with what we wanted to do, because wouldn't it be true that here we reach a tree that is higher, so this tree kind of hides our tree, but if we don't get to this condition, then our tree would be visible, right? Like if we exit the loop with an out of bounds condition, then our tree is visible. So we can probably maybe use that for our advantage. Yes, I think so. So let's see. Yeah, we have those answers. think that could be like, I don't know, sort of an improvement. I think, maybe. So we have this thing and we are mapping. Actually, we won't be able to be mapping and doing like something else inside of this map function. But yeah, it's tempting to do that. So let's try. Let's try. Visible trees, we are incrementing that. And visible trees was when, yeah, it is visible from the outside. And okay, maybe we can, let's first do something. Viewing distances, we can make this thing be a static array, let's say, of zeros, like 4 zeros. And instead of doing a map here, we can do a for loop for dx dy in directions iter, I guess. And here we have, these things will be references, I think. This, we can then, this is viewing distance, we can assign then. So viewing distance I is going to be this viewing distance. Okay, maybe I'm a bit sleepy at this point, it's 1 in the morning. So there is no variable I, of course, we have to enumerate these things. So we can get I and dx and dy. Why don't you like this? Because it's not declared as mutable, of course. It should be mutable. Okay, does this still work the same as before? It does. So we converted the map into a for loop. Very, very elegant. Functional programmers would really rejoice with this code. And now let's see what I wanted to do. So if we reach this out of bounds condition, we can know with confidence, I think that's the confidence I have, that this tree would be visible from the outside. So we say visible is true in this case, and let's then also have a usable variable visible that we can start as false. So we assume that trees are not visible, but when we try to look in any direction and we see that we reach out of bounds, we know that it is visible. So that's cool. And now with that we can say that we have the scenic score, but we also have, so let's order this in part 1 and part 2. So this is for part 1 and this is for part 2. This is for part 2 and now for part 1. If it is visible, then we are going to do simply visible trees, increment this thing. So we are doing a very, very imperative thingy. And I don't even know if we can... Dang it. my cat got scared and threw everything away. Simona, ¿qué pasó? Alright, I don't know why my cat got so scared. But she threw away a box that has a lot of guitar picks. Let's pick the picks up. And that's it. Mess solved. I don't know what's up with my cats today. They're a bit anxious or something. Okay, so I don't know if we can even do visible trees plus equals visible as bool. Can we convert things? No, as bool, no. As use size? Yes, it looks like it. That's pretty good. Do we have the same? No. We don't have the same answer, so maybe this cast, I'm not sure about this cast, so let's do the trivial code of before. Let's run again. No, that was not the problem. So, oh, because we are incrementing this twice. Was this the double than before? Yes, it's double the number, so actually we are doing the calculation fine, but we are doing it twice. So that was the problem there. Oh, look at this. 4, 4, 4, and loop. That's a nesting of 4 loops. That's really nice. But look at that. We still have the same answers, and now the code is shorter, which is the only criteria for good code, as everybody knows. Okay, so let's compare this to what we had before. So before we were doing things with iterators, and this declaration of the iterators was actually not that bad. But I sort of like, I didn't like this kind of thing. So in some sense, this is a sort of improvement, although it's very, very imperative code, I guess. Could we do something to improve, or to have like the iterator-based solution? We could have like maybe the 4 iterators in the order that they go to the outside, like we did before. But I'm not sure. You calculate the visible distances, and well, not sure. Not really sure. Do I like this code better than it was before? I think I do. I actually do. It is a mess of nested loops, that's for sure. But it's not so bad. It has its own structure, I guess. And yeah, it's not too bad. Actually, we can leave this thing plus equal visible as usize. We still have the same answer. Yes, indeed. And yeah, it's not too bad. The thing that I don't like about this solution is all the type coercion that we are doing here. Like, we are having these usizes, and then yeah, checking them. I guess we could do something like overflowing arithmetic here instead of adding unconditionally. So let's see, if we did something like x, there's a checked add. Oh, and this is receives an I32. Oh, yes, because it does receive an I32. So what could we do? I don't want to do a checked add in I32s, but I would like to we could use an overflowing add signed and pass the dx, and this thing, what does it return? It returns the number and bool. Whether the arithmetic overflow would occur. And what does it say about when it occurs? If an overflow would have occurred, then the wrapped value is returned. Yeah. I mean, we could use this and we would need this thing to be I size. Referencing the borrow, because yes, these are borrows. Now this would work. Stable library? This is unstable library, come on. So this thing expects a U size, but I don't want that. I would like to add a signed integer. So yeah, what I would like to do is something like this, and then for y do the same. Y overflowing add signed dy, and then instead of using this contains, now if it did the underflow, it means that you have gone to the moon to a high value. So you could say that if x is greater than the width, the grid width, or y is greater than grid heights, then it's that thing. But we do have, how do we get this? Really cool. So what do I want to do here? Oh, actually here we need to put this, extract this into like a variable. So actually for U size, I'm pretty sure that the wrapping behavior is guaranteed, I think. So if that's correct, then I don't know what the hell I am doing here. Because we could say something like x plus dx and y plus dy, and it won't like this because what? So x and y are u size. Yeah, now this whole thing we could cast again. I mean, I don't like any of these alternatives. The iterative solution seems a bit more interesting now. But also, I think it's also, I don't know, I want to try this and just have something more or less reasonable. So why don't I like this? Because we are using this, yeah, we're making kind of a mess here. So we want to wrap this thing, I guess. And if it underflows, I think the underflow behavior is guaranteed in Rust. Oh, but it will complain when in the debug builds. So that's not good. So I think like if I do, for instance here, I cast this thing as u size and trust the underflow behavior, I'm pretty sure I'm going to have failures on the debug. Yes. Oh well, it panicked because I guess here we can do this check to be. Oh, it actually didn't panic. Interesting. Why not though? Like, isn't there anything that goes to the left? Here we can have an unsigned, and then when we cast to u size, it will go to a very big number. So let's actually print if x is greater than, I don't know, 10,000 or y is greater than 10,000. Println x or y very big. So are we hitting that? Yes, sometimes they are very big. So it means that they did an underflow, and then when we cast it to u size, they get to be a very big number. And maybe I'm okay with that. Yeah. Is it kind of readable? I don't know. We can also keep, I think maybe it's better to keep x and y here as signed integers. So let's keep them. I don't really like this underflowing behavior is cute, I guess, but not very explicit. So let's keep this as eye size. Let's do this. Let's do this. Actually, let's do plus equals here. So this is fine. But now okay, you cannot compare this as this. Would you be happy if you are I32 instead of I size? Because that seems like something you could be. Not really. So let's say if x is less than 0 or x greater than grid size, or if y is less than 0 or this should be the condition. And I guess if we are using this here, we could have this as I size here and not worry about that. And this means it's visible. Viewing distance extends to the edge of the grid. Yes. And so the tree is visible. All right, and then what else? Aren't there any problems? Yes, this access to this slice, this should be as U size and as unsigned. Yes, indeed. Okay. So I went back and forth with the explicit conversions here. That's fine. Maybe we can put these directions into a constant, right? I think so. Viewing distance, yeah. Yeah, we can put this out of here, I guess, and make it a const. And what don't you like about this? Yes, directions in all caps, why not? And let's use it here. This should still be the same thing. Yes, indeed. And yeah, let's take a last cursory glance at the code and be happy with it. So we have the grid, parsing, then take the dimensions of the grid, fine. We make two variables to make the bookkeeping for the two parts, and then we return these things, fine. We iterate the grid, and we keep also other two mutable variables for if this tree is visible and the viewing distances from this tree, and we calculate those things. So I guess here, actually this variable, no, this variable is not really needed. We could just do the viewing distances, incremented them from here, and get rid of at least one of those mutable variables. This is visible, I think we do need, because here we are getting out of this inner loop, but not from this. So we can't increment visible trees in here because we would be like double counting if it's visible from multiple directions. We have the scenic score calculated by this. I don't know if there's a better way to do this in Rust, so let's look for it. Rust, multiply all numbers in iterator. Product. So there is a product, I think. Is it just called product? Yes. Very good. And that returns an I32 for some reason, because the viewing distances are I32s for another, again, for some reason. Oh, I guess this is the default. Right, that's fine. If we run now, still the same numbers. That's good. I learned about something new also. It's not called mult or something like that, it's called product. Nice. And the best viewing thing is this thing. Yeah, that's very fine. So okay, this code ended up being very imperative, but I think it's very compact and more or less readable, so I'm happy with this. I prefer this to the whole guacamole of repetition that we used to have. So, no, sorry, I had to compare it like this. Yes, we used to have this very repetitive code for each of the dimensions, for each of the directions. We now have abstracted over that, and by having an array of directions, this seems fine to me. Yeah. Let's add this change and let's commit this. So just add day 8 solution, and no need for anything else fancy on the commit message. I don't know what I typed there, so I'm pretty sleepy already. Man, this ended up being longer than I thought it would for a simple grid-based solution or challenge, but I guess we ended up refactoring things a bit to get a more compact solution, so I'm happy with that. Let's push the solution. And that's it for today's video. If you have been, thanks for watching and see you next time. Bye bye.